All right, today we're going to tackle a really classic and honestly brilliantly clever problem in computer science. How do you know if you're stuck in a never-ending loop? Let's dive in. It sounds a bit philosophical, right? But for a computer program, this isn't some deep thought experiment. It's a total disaster. It can cause a program to just freeze up and crash. So we're going to explore how to solve this exact problem inside a really fundamental data structure called a linked list. Okay, so first things first, we need to understand the path itself. We're talking about something called a linked list. The easiest way to think about it? Just picture a simple chain of information. Now, don't let the technical definition scare you. The concept is actually super simple. A linked list is just a series of elements, and we call these elements nodes. Each node holds a piece of data. But, and this is the important part, it also holds a little signpost, a pointer, that tells you exactly where to find the next node in the chain. So let's build one real quick. We start with node A, that's our head. Its signpost points to node B. Then node B's signpost points to node C. And here's the key. Node C's signpost points to, well, nothing. It points to null. And that null is the giant stop sign. It's the definitive signal that you have reached the end of the line. The path is complete. So that's the ideal scenario, right? A nice, clean path with a clear end. But things can get messy. Let's see what happens when we introduce the very problem we're here to solve, the infinite loop. What happens if that final signpost, the one that's supposed to be our stop sign, doesn't point to null? What if instead it mischievously points back to an earlier spot in the chain? Well, this is where our program gets into some serious trouble. Normally, a program would just start at the head, follow the pointer to the next node, and then the next, and so on, until it hits that null signal and knows, okay, my job is done. It's simple, it's clean, and most importantly, it's finite. But with a loop? Oh man. Our program starts walking the path and it just keeps walking. It follows the pointers, it gets to what should be the end, but then, whoops, it gets sent right back to an earlier part of the list, completely unaware it's now destined to walk that same circle of nodes forever. It's trapped. It's a hamster on a wheel. So how in the world do we detect this invisible trap without getting stuck in it ourselves? With a wonderfully elegant solution known as Floyd's cycle-finding algorithm, or as it's much more famously known, the tortoise and the hare race. Here's the plan. We're going to send two runners, which are really just pointers, down our linked list. First up is our slow pointer, the tortoise. It moves just one node at a time, steady. Then we have our fast pointer, the hare, which leaps forward two nodes at a time. The rules are really that simple. And here's the entire idea in a nutshell. If the linked list is just a straight path, the hare will just get to the end first. No big deal. But if there's a circular track somewhere in that path, the fast-moving hare is guaranteed to eventually catch up to and lap the slow-moving tortoise. If they ever land on the very same node at the same time, we've just proven a loop exists. Okay, let's watch this in action. And they're off. They both start at the head. After the first step, our slow pointer is at the second node, B, and our fast pointer, having jumped 2 spots, is already at node C. On to step 2. The slow pointer plods along to node C. The fast pointer takes another 2 big leaps and lands all the way down at node E. It's pulling away, just like you'd think. And now for the magic. Slow moves to D, but the fast pointer, from E, hits that sneaky last node that loops it all the way back around to C. Whoa, the hare has now entered the circular part of the track. Okay, pause. This is the key moment. The dynamic has totally flipped, even though the hare is ahead in terms of moves made, because it's now on the same circular track as the tortoise. It's effectively behind the tortoise on this little loop, and it is closing the gap with every single step. And just 2 steps later, bam, collision. The slow pointer arrives at node E. The fast pointer, zipping around the loop, lands on that exact same node. They've met. The race is over, and we have definitively 100% proven that a loop exists. So this brilliant concept isn't just a cool idea. It's something we can write in just a few lines of actual code. Let's see how this whole tortoise and hare race translates into a C programming function. Now, you don't need to be a C expert to get this. Just look at these highlighted lines. This is the heart of the whole thing. Slow equals slow.next. That's our tortoise moving 1 step. And fast equals fast.next.next. That's our hare taking its 2-step leap. It's a perfect literal translation of our race.
The entire race happens inside this while loop. You can think of this line as the safety check. It just makes sure that if the list is a normal, straight path, our fast pointer doesn't try to jump off the end into nothingness, which would totally crash the program. If there's no loop, this condition will eventually fail, and the race just ends peacefully.
And this right here, this is the finish line. Inside that loop, with every single step, the code is asking one simple question. Are the slow and fast pointers at the exact same memory address? The moment slow equals fast is true, we have our answer. We found the loop. So why do programmers and computer scientists get so excited about this particular solution? I mean, it's not just that it works, it's how it works. It's an absolute masterclass in efficiency. What makes this algorithm so special is it's just jaw-dropping efficiency. First, it's speed. It's fast and predictable. If the list gets twice as long, the algorithm takes roughly twice as long. No crazy slowdowns. But here's the real genius. It's memory usage. Think about it. You could have a list with 10 nodes or 10 times billion nodes. This algorithm needs the exact same tiny amount of extra memory to solve the problem, just enough space for our two runners. That's it. It's so elegant, it's intuitive, and that's why it's a foundational concept in computer science. So we've successfully detected the loop. We know it's there, but that leaves us with another fascinating little puzzle. We know there's a circular track, but how would you pinpoint the exact node where that loop begins? Now that's a great question to chew on.